The arrangement of electrons around the outside of the nucleus can get a little complicated. Electrons actually exist in these three-dimensional clouds around the outside of the nucleus that we call orbitals, and they can get quite complex. Another way to define orbitals are areas where electrons are likely to be found at any given point in time. Orbitals can have these different shapes. They can be spherical or have these weird kind of balloon animal shapes. And as you begin to combine atoms together and make molecules, the shapes of these orbitals can change. So they can get quite complex. Now for our purposes, I just want you to know that these orbitals exist, that they are spaces where electrons are likely to be found. We're going to focus more on the energy levels at which electrons can exist, something called shells. Another aspect of the arrangement of electrons within an atom, and the aspect that we are going to focus on, are these things called electron shells. Now, shells don't have so much to do with the actual physical location of an electron, so much as the energy that it has. So I want you to think of an electron shell as being kind of like an energy layer around the outside of the nucleus. Here, for instance, you can see one shell, and it has a certain distance from the nucleus. Ooh, that's terrible. And here's, oh, it's even worse, a second shell, and it's a little further out from the nucleus. So these are energy layers. Now, what kind of energy does this represent? It represents potential energy. And electrons that are in these different layers can have different amounts of energy. They will also be a different distance from the nucleus. Now, as I said, these different electron shells have different amounts of energy, and here we're talking about potential energy. Shells that are closest to the nucleus actually have the least amount of potential energy. In other words, they have the least potential to leave or to jump up to another energy level. And that's because this big old nucleus with its protons in here is holding very tightly to those electrons. It's attracting them most strongly in the first shell. Electrons in the second shell have a little bit more energy, in the third shell have even more energy, and so on. The further away from the nucleus, the more potential energy an electron has. The more potential it has to jump up to another level or to leave the atom entirely. Now, electron shells are arranged kind of like seats in something like a stadium or a concert arena, something like that. What do I mean by that? Well, if you've ever been to a sporting event or a concert, you know that the really good seats are right up here next to the stage or right up here next to the field. And those are really expensive because they have the fewest number of seats. In the same way, the shells that are nearest the nucleus can hold the fewest electrons. Those are the really good seats. If you go back a few rows, well, those rows are actually bigger, so they can hold more electrons. And if you go way back here into the nosebleed section, well, those are the cheapest seats because they can hold the most electrons. So these different energy levels can only hold certain numbers of electrons, and that number tends to increase as you go from the nucleus out. Here's another really fun example or illustration of this concept. Here we have a balcony. This balcony is going to represent our first shell that's nearest to the nucleus. This shell contains one old person. It has room for 2 old people, however, and so now that a second old person has joined the first, that shell is now full. There's no vacancy there. So an atom that has more than 2 electrons has to have a second energy level, a second shell, to hold that third electron. So each electron shell can only hold so many electrons, and in general, the closer to the nucleus it is, the fewer electrons it can hold. Here are the rules for the first 3 shells. Shell number 1, which is closest to the nucleus, can hold 2 electrons, and that's it. So if an atom has more than 2, the rest of those electrons have to go to the next shell. Shell number 2 can hold an additional 8. So an atom with a maximum of 10 could use those 2 shells by themselves. And then the third shell can hold a maximum of 8 electrons. Now, if you are very chemistry savvy, you'll know that that third shell can actually hold 16. But after we have a maximum of 8 in that third shell, the electrons tend to start jumping up to the fourth shell and doing some weird things. So for our purposes, we're going to think of the numbers as being 2, 8, and 8. There's only one example of an atom that will get larger than this, that's calcium, that we will use in this class. So we're going to stick with the easy numbers here, 2, 8, and 8. Here's a couple of examples of different kinds of atoms with different sizes that use different numbers of electron shells. Here we have good old hydrogen again, super tiny hydrogen. It has one little electron, so it can put it in its first shell, and it's perfectly fine like that. Now you'll notice that hydrogen actually has room on its shell for one more electron if it can find it somewhere, because that shell can hold 2. Carbon, on the other hand, has an atomic number of 6. So in its natural state, it's going to have 6 electrons. It's going to put 2 on the first shell, and now that shell is full. It has 4 additional electrons, so it's going to put them on the second shell. Now let's think about this. Is that shell totally full? Well, no, because the second shell can actually hold 8. So potentially, carbon could put 4 more electrons in that shell. And that's going to be how it begins to make things like covalent bonds, which we'll get to in a little bit. These diagrams, such as the one shown here, are known as shell models. And shell models are useful because they show the number of shells that an atom uses and the arrangement of the electrons. So this, for instance, is the shell model for carbon. Now, the shell of most interest is this one out here, and I'm terrible at tracing, but you get the idea. This is known as a valence shell, and valence shells are important because when 2 atoms get together to make a bond, to make a molecule, these are the shells and the electrons that are going to interact. So it's important to be able to identify the valence shell of an atom. In this your turn, I'd like you to use what you've learned about the arrangements of particles inside atoms to draw some shell models. So I want you to draw the shell models for oxygen, nitrogen, phosphorus, and sulfur, and bring those to class with you so we can compare them and discuss them.